continue with the example of fully developed flow through a circular pipe, and we in the last class arrived at the simplified forms of the governing equations. So let us continue with the governing equations which are written here. First let us consider the R momentum equation. So in the R momentum equation, first of all let us see that what is this BR. See, BR is the body force component in the radial direction. There is a body force component in the radial direction, that is true, but until and unless this extent of the pipe is very large, it is like a very high radius pipe, then that effect of that body force is not going to be important along the R direction. So this therefore may be neglected. So you come up with the pressure gradient along R equal to 0 or approximately equal to 0. That means P is not a function of R only, not a function of R, that means P is a function of Z only. So you can write, when you come to the Z momentum equation, this as dP dZ, and you may combine that term with the body force term to have d dz of P plus rho gz sin theta is equal to mu into 1 by R ddr of R dvz dr. Because Vz is a function of R only, that we showed in the last class, therefore it boils down to an ordinary derivative. So this P plus rho gz sin theta is like P plus rho gh, so this is like P star, the piezometric pressure. We again are having an equation where you have dP star dz is equal to mu into 1 by R ddr of R dvz dr, where the left hand side is a function of Z only, the right hand side is a function of R only. So this is function of Z only, this is function of R only, and again this may be valid if each is a constant. So each equal to constant say equal to C. So the first thing that we may do is to find out the velocity profile from this. So we consider the right hand side and integrate it. So you have d of R dvz dr is equal to C by mu R dr, right. So this you may integrate. So once you integrate, you have R dvz dr is equal to C R square by 2 mu plus C1, which means dvz dr is equal to C R by 2 mu plus C1 by R, okay. So you may integrate it once more. So if you integrate it once more, you will get Vz as a function of R. So let us do that. So you have Vz equal to C R square by 2 mu plus C1 ln R plus C2, sorry 4 mu, yes, 4 mu plus C1 ln R plus C2. Now C1 and C2 are the constants of integration that we have to find out from the boundary conditions. So what are the boundary conditions here? Boundary conditions. So one of the boundary conditions, that is at the wall, is straightforward. At small r equal to capital R, you have Vz equal to 0, no slip boundary condition. Then what happens at small r equal to 0? That is a point of singularity, so to say, and but physical problem is that Vz has to be defined at small r equal to 0. I mean you can't have a situation where there is Vz undefined at small r equal to 0, because it is a physical problem, the pipe is entirely filled up with fluid with some velocity, at r equal to 0 there should be a well defined velocity, and that is possible. So Vz is at r equal to 0, Vz must be finite, it cannot be infinite or it cannot be undefined in other words. Therefore from the second condition you must have C1 equal to 0, this is from the boundary condition number 2, and from the boundary condition number 1, so this is boundary condition number 1 and this is boundary condition number 2. So from boundary condition number 1 you have 0 equal to C r square by 4 mu plus C2, that means C2 is minus C r square by 4 mu. So the velocity profile becomes Vz equal to C by 4 mu into, or if we write minus C by 4 mu into capital R square minus small r square, right. And as usual you see that the C which is like dP star dz, that has to be negative to drive the flow along the positive z direction, which means that Vz has to be positive if C is negative. Now you may express C in terms of the average velocity, what we did for the plane Poiseuille flow, for the Hagen-Poiseuille flow also the same thing is valid. So what is the average velocity? V average, it is integral of Vz over the area of cross section divided by the area of cross section. So Vz, what is the area of what is the elemental area that you can choose, say at a distance r you take a strip of width dr. So if you just draw its other view, so you have taken at a radius r some strip, so you are talking about such a strip of width dr, and this strip is 2 pi r dr. So Vz into 2 pi r dr from 0 to capital R divided by pi capital R square is the area. So let us do this integration quickly. So 2 into integral of 0 to r, you have minus C by 4 mu So what is V average in terms of C? So minus C by 2 mu, then if you integrate it, so R square, so R4 by 2 minus R4 by 4 by pi R square, sorry pi is not there, pi has got cancelled, right. So this is equal to minus C r square by 8 mu, right. So this is one important result which we will use subsequently, but at least let us write the expression for the velocity profile by writing C in terms of this. So Vz becomes, in place of C you write minus 8 mu V average by R square, that into 1 by 4 mu, again there is a minus sign, into R square minus small r square, that means Vz by V average is 2 into 1 minus small r square by capital R square. This is the velocity profile in terms of the average velocity. recall the flow between two parallel plates, it was like 3 by 2 into 1 minus y square by h square. So, it is quite similar, the coefficient is different just because of the different geometry, and it is also a parabolic type of velocity profile because it is square with the local radius. Now, you can find out the what is the wall shear stress. So, let us find out what is the wall shear stress. So, it will be like mu, we will adjust the sign positive or negative later on, mu into the rate of deformation. This is like tau rz. So, the proper subscript with the index. Now, one of the important things is see positive tau which is like mu du dy. So, this is like just like mu du dy. First of all Vr is 0, so this term is not there. So, it is just like mu du dy, but the thing is see the r direction is towards the solid boundary, it is not away from the solid boundary. So, that has to be compensated with a minus sign here. So, if you have a solid boundary like this, if you have this as y, then you have like du mu du dy. So, y is away from the solid boundary towards the fluid. The reason is you want to write it as a positive shear stress. So, you want u to be increasing in the y direction. So, y equal to 0 is like the no slip and then u increases, but here the r direction is opposite to that. So, you have to make it up with a minus sign. So, the wall shear stress therefore, if you just differentiate it with respect to r, so dVz dr is like 2 V average. So, this entire thing evaluated at small r equal to capital R, that is at the wall is located at small r equal to capital R. So, 2 V average into minus 2 so minus 4 V average by R is the dVz dr, right. Therefore, the wall shear stress is 4 mu V average by R. What is the coefficient of friction or the Fanning's friction coefficient? That is tau wall by half rho into V average square. This we introduced in one of our previous classes, this friction coefficient. It is a non-dimensional way of writing the shear stress. So, it is 4 mu V average by R, basically it becomes 8 mu V average by R rho V average square. So, it is 8 divided by rho V average R by mu. The denominator is a Reynolds number based on radius r, but usually for this type of geometry the length scale that is taken is 2r or the diameter of the pipe. So, if you just consider that, then the Cf becomes 8 into 2 divided by rho V average into the diameter by mu, where diameter is 2 into r. So, this is 16 by the Reynolds number based on the diameter of the pipe. Now, what as engineers what we want to do with this friction coefficient. So, what importance or implication it has to us. So, if it is large, it is small, we may understand that if it is large maybe the frictional effect is large, but how do we take care of that in a design, and that may be visualized more effectively if you consider now the dP star dz term which is equal to C. So, to do that let us come back to this equation V average written in terms of C. So, what is C? C is equal to dP star dz. So, let us write dP star dz in terms of the other parameters. So, it becomes minus 8 mu V average by r square. Okay. So minus 8 mu V average by r square, and what is this dP star dz? This is if you have pressure at the inlet as say P in, if you have pressure at the outlet as say P out, and the distance over which this pressure difference is there is L, then first of all we could derive that dP star dz is a constant. That means P star versus Z is a linear profile. So this is as good as P star out minus P star in by L. Okay. So this we just write as P star out minus P star in by L. So in other words it is minus of P star in minus P star out by L. I mean, why we are writing it in this way is, see, the P star in minus P star out is the driving delta P star for the flow, the driving difference in piezometric pressure that should drive the flow. See, why this driving pressure difference is necessary? It is necessary because you have viscous resistance in the flow. So this is a manifestation of the consequence of the effect of viscous resistance that is being exerted in the flow. So you have to have a driving pressure gradient which is a favorable pressure gradient, that is dP star dz negative, to make this flow occur. So when you have this one, this delta P star, so what it in effect does? In effect it overcomes the viscous resistance. So the viscous resistance also may be expressed in form of a pressure unit. So the viscous resistance, therefore you may say that delta P star is nothing but the delta P star because of the viscous resistance, and we may write it in terms of a head or some unit of length. So we remember that the pressure is nothing but some length unit into rho into g, and the length unit is the equivalent unit of pressure expressed in terms of length which we call as head. So that is what we discussed also earlier. So if we write it in terms of a head unit, length unit as head with a subscript h, f for friction, so we can write it hf rho g, where this hf, as engineers we understand that this is a loss of head due to fluid friction. Okay. Therefore it is possible to write this expression dP star dz, if we come back here, in terms of this delta P star as hf rho g. So you have hf rho g by L is equal to 8 mu V average by r square. Okay. Of course it is possible to write it in terms of the diameter. So it is so 8 becomes 32 here. Okay. So it is also possible to write the average velocity in terms of the flow rate, that is sometimes important, because if the flow rate is q, it is just q by pi d square by 4, because in the experiment you usually measure the flow rate. So it is, we are trying to write the equation in terms of experimentally measurable parameters. So from this what you get is hf is equal to 128 mu ql by rho g pi d to the power 4. Okay. And this equation is known as Hagen-Poiseuille's equation. So what it gives? it gives a direct indication of the loss of head due to viscous effects in the flow. If the flow had viscosity 0, there would have been no loss of head, and we can see that the loss of head is directly proportional to the flow rate. It is proportional to the length over which the fluid is flowing, which is understandable, and inversely proportional to the fourth power of the diameter. So if you make the diameter very small, the loss of head will be very large. That means to drive flow through a very small tube, say a tube of micron size, you require a huge pumping power, because there is a huge head loss because of the frictional effects. That is one of the challenges in having a flow in a micro or a nano channel, in a very small channel. So the whole understanding is that like those are advanced topics, but you see that the basic of fluid mechanics gives us a clue that what are the challenges as you make the sides smaller and smaller, what are the engineering challenges in terms of having the flow. Now it is also possible to express it in terms of a non-dimensional form by writing this in this way, by writing this as some factor f into L by d into V average square by 2g. So this is just a non-dimensional way of writing it. See, L by d is a sort of aspect ratio of the pipe, it is a non-dimensional parameter. So and V square by 2g is the kinetic energy head. So the head loss expressed as a fraction of the kinetic energy head, this F is that sort of fraction. So what is that? So if you just equate these two, so you have HF as rho g rho F L by d V square by 2g, and that is equal to whatever expression of HF what we had. So 32 mu V bar by d square L by rho g, right. So from here what we can conclude, what is F? 64 divided by rho V bar into d by mu, okay, by equating these two. So that means this F becomes 64 by the Reynolds number. So this sort of non-dimensionalization was first introduced by an engineer known as Darcy. So this friction factor is also known as Darcy's friction factor. So it is just a different way of writing the friction or frictional coefficient. You can see clearly that F and Cf are related by F is equal to 4 into Cf. So just is the same thing expressed in terms of in different ways. So one looks into it in the viewpoint of a pressure drop, another looks into it in the form of a wall shear stress, and here they are related because you have to overcome the wall shear stress and therefore you have a pressure drop. So that is how they are related, and this 4 coefficient is just because of the difference in which they are defined, but physically they imply the same. So if it is Manning's friction factor, that is Cf, and if it is Darcy's friction factor, it is F. So now so we have a clear idea that if we have flow through a pipe, there is a head loss. The head loss is because of the viscous effects in the flow, and you require a driving pressure gradient. The driving pressure gradient is to overcome an energy loss. The energy loss may be expressed in terms of a head, and that head is given by this expression. So that is what we learned, and as engineer it is important because say you are given a length of the pipe. See, I mean, let us think about how this helps in design. Say you are given a length of a pipe, say 10 centimeter length of a pipe. You are given a flow rate that you expect out of it, say some meter cube per second. You know what is the viscosity of the fluid and density of the fluid like that. So your problem is that what should be the power of that pump that is necessary to drive the flow. This is one of the very basic elementary problem. So to know that, you have to know that what is the pressure drop that is taking place, and first of all if you find out what is the HF, what is the head loss over that length, then that into rho into g is the pressure drop, and the pump should have enough power to overcome that. So, the pump should have a power that is developed, that is given by rho g into q into the head loss, it has to overcome that loss. So, this is like a unit of power. So, if you know that what is the flow rate, if you know what is the head that the pump has to supply, then you know that what is the power of the pump that is necessary. And so, it comes into, so a very basic elemental mathematical work also is necessary even for a very crude design work which is there in the day to day life of fluid mechanics, like flow through pipes. Okay. Now we come to another example, example 5, and that will be like the final example before we will be moving to the next chapter.